Cool. Yeah, if you would that. You can see.
Speaking, my mic would be here with the laptop. Oh, mic for this. So why did I unmute my mic?
Yeah, please.
Yeah,
because the recordings
So should I mute my audio?
So it has to be.
Oh, it was muted before.
Yeah.
Oh, wait,
Yeah.
All right, let's bring it back. Bring it back to the front. So, if you think the left diagram best represents the memory. Okay. Now, if you think the right diagram best represents the memory. Like none. But you guys are all correct. Here, it is the left diagram, right? In OCaml, all of these values are heap allocated. So when we make the strings here, on the heap. When we make this array here, on the heap. You might think, like if you come from C, that if you make this array here, it'll be stack allocated. But no, heap allocated. But we want to change that. We don't want this heap allocation, right? So this function is named really, really well, because what bad thing could happen given all of these heap allocations in this function? Just shout it out. You don't even have to raise your hand.
If the array is returned, if the array is returned, then
if the array is returned, okay, but if I just have these allocations and my function is performance critical, what might happen?
Yeah.
GC, we have a garbage collector, right? Someone's got to look at these things. There could be a garbage collection cycle, and relatively speaking, that is a slow thing. And so if we have this performance critical function, maybe we're like trading a bunch of money, then we don't want the garbage collector to interrupt us. But if we want to avoid these allocations, going back to the answer in the back, what would the compiler need to know and do to avoid them? You can also shout it out. An escape analysis. Why an escape analysis?
if we don't return the array, there's no set, right?
Right? If we don't return the array, the code's gone. If we don't return the array, then we know that we can safely locally allocate the array, and then we avoid that allocation. So we can perform an escape analysis, and then the second thing we need to do, this one's obvious that it's hard, is you actually have to update the code, right? You can run an escape analysis, you can say, symbols doesn't escape the function, but if you don't actually go and update the code to make that a local allocation instead of a heap allocation, then you could still have some allocations there. Now, OxCaml provides both of these facilities for us, so we're going to walk through how these work. In this code, we want to assert that symbols does not escape the function. And how we do that is we use this @local syntax. Right? So this is telling the compiler, hey, we expect that this thing does not escape the function. And then the compiler will check that for us. So if we did try and return symbols, it would say, hey, you said this thing doesn't escape, but it's escaping. That's bad. And it turns out every value in OxCaml is either local or it's global. Global are all of the values that you have in OCaml. That is sort of the default thing. Right? These values can live forever. They're global. But if we say something is local, then we're telling the compiler that that value doesn't escape the current region. And if people have questions, just like raise your hand and stop. This is totally interactive as well. And then the key thing is that a value that is local could be locally allocated, right? This is the escape analysis portion of OxCaml. Now, this is not actually updating the allocations, it's just doing the escape analysis. So now let's go in and add the actual local allocation. So we want to ensure that symbols is locally allocated. And we do that with one of two keywords, stack underscore or exclave underscore, and we'll explain both of these. So stack underscore, we can put right here. Right here. I can write on the slide, so I'm going to use it as much as I can. We're going to put it right there. And what this is telling the compiler is, hey, we are going to locally allocate this expression. And I have this at local here, because this is telling the compiler, hey, symbols doesn't escape the current region. But I can actually add stack here and leave out the at local, and the compiler knows that symbols is at this local mode. All right. So there's one little technical bit that I'll have to explain, and this is something called the local region. But I've been careful to say locally allocated instead of stack allocated for one specific reason. So when we have our perf critical function here with the stack keyword, that looks something more like this Rust code on the right. I don't expect you to know Rust. You don't need to know Rust. Rust just makes explicit what the OCaml code is making implicit. So implicitly in this OCaml code, we have a local arena allocator attached to every function. And when we say stack underscore array, what this means is we're going to locally allocate that array in our arena. It's right here. And so when the function ends, everything in the local arena also gets cleaned up. There's no garbage collector involved, but it is still a dynamically sized arena allocator there. All right. So I've given you some partial information, and I'm interested to know, with the information you have currently, which of these diagrams best represents the state of memory now in this perf critical function using the stack keyword? Talk to your neighbors, and then we'll vote in a second.
Yeah, because it's specified a local.
I'll tell
I guess here's the arena.
There's another.
All right, let's come back. I hope everybody has an answer in mind. So let's go ahead and vote. Who thinks, by way of humming, the top diagram represents the state of memory after binding symbols? Okay. Who thinks the bottom diagram represents the state of memory after binding symbols? Oh, like 3 people? Okay. Why somebody over here hummed? Why might this be the diagram? I said might. I'm giving you the answer. Yeah. Why might this be the diagram for the code?
Well, I thought that the array is local, then the variables inside.
Yeah, the array's local. Why not allocate the stack and the strings locally, huh? That'd be great. So it turns out the answer is the top one, because stack only controls the allocation for the array expression. Gensim, which is a separate function, still allocates the strings on the heap. And we can actually analyze this just from the type signature. So this is the type signature of Gensim. It goes from unit to string. And I'll remind you that every value in OxCaml is either at local or at global. And implicitly, because the default for OCaml is at global, what this means is the return string is at global. So Gensim is going to allocate its string on the heap and return that, and that's totally fine. Local allocation will require cooperation from all of the callees. So if we want Gensim to allocate locally, we have to change the implementation a little bit. And here's how we might do it. So we're now going to abstract our array creation into a separate function called gensim2. Just does the same thing, right? Creates the array, gensims, and returns them. Now, if we run this code, well, it doesn't run. There's a compiler error. And it says that the expression is not an allocation site. Because just calling gensim2 the function, that expression itself is not doing any allocation. It's the code inside of gensim2 that is doing the allocation. So we might be able to move stack, up into the implementation of gensim2, but we get another compiler error. And what this says is the value escapes its region. So this goes back to what I said earlier. When we write stack underscore, that makes that value local to the current function. And we don't want the array allocated locally to gensim2 because we do need to return it. We want it allocated locally to the perf critical function. And that's exactly, some Rust code before we get into that. The equivalent of this code is, allocating something in the local arena and then returning that pointer, which is unsafe. Because as soon as we leave that function, once we hit that curly brace, the local arena is going to get cleaned up and all the memory in it, and we would be returning a pointer to that memory. So that is a dangling pointer there. So how we actually do it is we use the exclave keyword. And what that means is it's going to allocate the value in the caller's local region. So this is sort of what the memory might look like here. And when we allocate this array, we do it in the caller's local region, right? So there's that horizontal bar dividing the two local regions. And when we return from gensim2, its local region gets cleaned up. And then we have the array properly allocated in the local region for perf critical. Nice. Now, this code is sort of a similar variant of everything we've seen so far, right? I'm going to locally allocate a tuple of strings, and then I'm going to return the first element of that tuple. And of course, this would be incorrect code because that string could be locally allocated. And so we'd be returning a dangling pointer here. I forgot to mention these confused OxCamls in the corner mean that the code doesn't compile. So if you ever see that, it means the code's not compiled. Now, if we rewrite this function to use genInt, gensim's sort of estranged cousin, it's just a counter, right? And we return the first element of the tuple, even though it is locally allocated, this code does compile. Wow, you're shaking your head like you're really agreeing.
It's immediate. It's an immediate the return register.
Yeah, right. Integers are not allocated values. They're just on the stack. So instead of returning a pointer, we're actually just returning the integer. So it's safe to return a locally allocated integer, or because there's no allocation. Locally allocated integers and globally allocated integers sort of mean the same thing. They're just integers. That's what I just said. All right. Now, when we're writing our code, we might want to ensure that a function is zero allocation, right? If we have a really performance critical function. And OxCaml comes with a set of extensions. One of them is this @0alloc attribute. And so we can put this on our functions. And then the compiler will tell us, hey, this code here, this array.init, calls camel make vect, which is the function to globally allocate the array. And zero alloc uses some abstract interpreter to check if the extent of your functions is zero alloc. So it will check function and the functions you call. Right? A lot of the functions that are provided from the standard library or base come with versions that locally allocate things. So in the current version of OxCaml, you would write @alloc stack after array.init, and that's specifying that we want the version of array.init that locally allocates the array. Now, this is something that is most likely going to change in the language, so don't get too attached to the syntax or too dissuaded by the syntax, but that is how you currently would specify it. But it turns out this code also doesn't compile, right? Because we never changed gensim. Gensim still allocates those strings on the heap, and we'll leave that as an exercise for later. All right. So far in our whirlwind tour of OxCaml, we've seen new keywords like stack and exclave, which give you control over the memory allocation. We've also seen these annotations @local and @global. And these things can appear on let bindings, but they can also appear in type signatures that specify the local or globalness of the values being returned there. And local and global are instances of what OxCaml calls modes, which is the major change to the type system over OCaml. And modes are how OxCaml provide safety. So let's talk about modes for a little. In OCaml, we have a whole bunch of values. So we have things like these over here, which we call broadly strings. And then we have integers, and we have floats, and we have arrays and lists of things. And types give us a way to ascribe properties to a value, right? So if we have a string, we know that that value is immutable because strings are immutable in OCaml. If we have, an integer, we know that that is not allocated and it's just an immediate value, etc. Right? Strings give us properties of these values. Modes also ascribe properties to values, but they ascribe properties that make sense for a whole bunch of different types. So for strings and floats and arrays, I can say that these things are local. And I could have drawn this bubble around any subset of these values, and it still would make sense. So our broad definition of what is a mode is that modes are deep properties of values. You can read that for a second. Now, when we say deep, what we mean is if you have, an array of floating point numbers, not only is the array assumed to be local, but also the elements of the array, right? Types are not deep. I can have an array of floats, and both of those types describe the different elements, but here modes are deep. So if you have an array of something, the array and the elements are assumed to be at that mode. Now, example properties of what modes might give you is things like a value doesn't escape the region, the local mode. We can say that a value is unique. So there only exists one pointer to this value. A function may be called from any domain. If you're not familiar with OCaml, that's synonymous with thread here. A function can be invoked at most once, and lots of other properties. And modes provide the safety to OxCaml. So we're going to talk about data race freedom in a second, and we just talked about memory safety. Now, a bit more formally, the locality axis is what we've just been talking about with stack allocation here. So the locality axis has two modes. There's the local mode and there's the global mode. And there's actually a sub-moding relationship between these. So here we would say that global is a sub-mode of local. And that is how this code was able to type check earlier, right? We have the local symbols, but we don't have the stack here. And we don't have the exclave here. Right? So nothing is actually doing this local allocation, but we can say, symbols is local, it doesn't escape the region. It's just an escape analysis. And then every mode has a default for OCaml values. For the locality axis, that default is global. And in these tables, I will highlight or bolden the defaults. And we call the @local a mode annotation. Questions up to here? Eric. Good. So mode crossing is this thing that we saw earlier where we said integers at the local mode and integers at the global mode don't make a difference, right? Because integers aren't allocated here. And so this works, like this code here works, because integers cross locality. And what that means is an integer is the same at local and global. And there are values that cross along a lot of the other mode axes. And we'll see some examples a little bit later. All right. And the high level takeaway from here is that mode crossing happens when the type, the properties of the type, actually work with the properties of the mode. So we know because integers aren't allocated, they can mode cross freely along the locality axis. That's our sort of theory. That's it. All right. Now we're going to get into some parallelism. Actually, let's take a 5-minute break really quick. Talk to your neighbors, 5-minute break, then we'll talk about parallelism. Go. Are you in?
That's like extreme violence. Like violence. I got it to yoga for my back.
Takes a while.
But if you want like that, okay.
It's like 15 or 16.
All right, let's come back. We're coming back. All right, so OCaml 5 is incredible. There's a lot of people here that worked on it, and it introduced true parallel programming with a multi-core aware runtime effects. But it woo! But it also unleashed chaos, right? My life is now hell because I have these race conditions and databases and non-deterministic bugs and all this hard to reason about code. So it's good, but it's also bad. And we want to tame all of these bad things here. And we want data race freedom. I don't want to be sure that my code has no data race. So OxCaml introduces two mode axes that work together. And these are called contention and portability. So we're going to modify our gensim example again. And now we have this gensim n function that is going to generate an array of length n. And then you're going to have all of your gensims. Now, this uses the parallel array module. So when it calls init, it's actually going to evaluate all of those functions in parallel for each of the elements of the. All right, now I want you to talk to your neighbor and come up with some bad thing that could happen if I call gensim n with an n that's greater than or equal to 2. Discuss.
I would like to be Krishnamurthi. Oh, yeah.
You're in good company.
Actually, don't
That is not as common.
Let's come back. A lot of good discussion. Who wants to tell me what they talked about? What bad thing is going to happen here or could happen?
Data race.
Data race. Okay, what could happen if there's a data race?
Identical symbol.
Identical symbols, right? Gensim is supposed to give me a unique symbol, but now, right? Here's a little example. We have one domain running on the left. It might read the count variable at 0. Our other domain is running on the right. It also reads count at 0. Okay, now on the left again, we're going to increment it from 0 to 1. On the right, same thing. And now when we read it at the end, count is 1 on both domains. And that means that our array has 2 gsim 1s. And that is bad. So my code was not expecting that, and it breaks. And I don't know why it broke, and now I have to debug it. My life is hell. So it is unsafe to run gensim on multiple domains. And we want to statically prevent this from happening. So we might reason about this by saying that. Sure. Okay. Backing up a little. A data race requires 4 ingredients, right? There needs to be parallel execution. We have to actually have things running on 2 domains. There needs to be some shared memory. That's a location accessible by the domains. There needs to be at least 1 write. And there needs to be no synchronization on the memory. So if we pull back up the gensim function, we can identify all 4 of these ingredients, right? So this ref0, this is our shared memory. Bare references do not provide synchronization. Then we have, let's see, right here, we have our write and our read from count. And then we have another read here. And then, of course, if n is greater than 1, we have some parallel execution. So we might reason about this by saying, well, this lambda, right? This lambda. It must be safe to share across domains. And so therefore Jensen needs to be safe to share across domains because that lambda calls Jensen. We say, well, Jensen closes over this non-synchronized mutable reference and reads and writes to it. So that's bad. So Jensen is not safe to share across domains. Therefore, neither is the lambda. Right? That's sort of like the high level reasoning we just went through. But when you have a really large code base and you have different modules, that's harder to do. So we introduced these mode axes for expressing parallel constraints. So the first is portability. And the question that portability asks is this value, but really we only care about functions here, is it safe to share across domains? Now, the portability axis has two modes, portable and non-portable. Portable means, yes, I can share it across domains. Non-portable means no, I cannot share it across domains. So if we have a value that is non-portable, the property that we assign to that value is that the value isn't shared across domains. Right? And so if we look back at our function and we annotate Jensen as saying it needs to be portable, the OxCaml compiler is going to say, well, it isn't portable, and I'll show you the error in a second. And it needs to be portable because the type signature for the par array init right here requires that that function f is portable. Okay. All right. Now, the second mode axis is contention. And what contention asks is, what access do I have to this shared memory? And there are three modes in the contention axis. So one of the modes is uncontended, meaning I can freely read and write to it, right? It's uncontended. There's the shared mode, which means that I'm sharing it with a bunch of other domains. So I can read from it, but I cannot write to it. And then there's contended, which means it's shared with a whole bunch of other domains. And so I can't read or write to it. And the assumption is that if there's a contended reference somewhere, someone might have an uncontended reference to that value, right? So if there's one uncontended reference to the value, someone could be reading and writing to it, so nobody else can. So the property of a contended value is that the value isn't read or written. The property of a shared value is that the value isn't written. And then the property of the uncontended reference is we don't know, anybody can do whatever. So I'm just going to shuffle the rules a little bit. And there's one very important rule that ties the contention and portability axes together. And that is that references captured by portable functions are contended. So in this function, right, we expect that Jensen is portable, but it captures the count variable, right? Count reference here, and here, and here. And so inside of the function, count is inferred as contended. It is a contended reference because multiple domains might have access to it. But we're trying to read and write to it. So the compiler is going to say, well, this value is contended, right? It was closed over in a portable function, but it's expected to be uncontended because you're doing all this stuff to it. And so the compiler has cleverly caught our shenanigans, right? We're trying to read and write to something that is shared across multiple domains. So we may want to actually safely work with mutable state. And for this, we have atomics, and we also have capsules. Now I'll explain sort of what both of those things are. So atomics are exactly what you'd expect here. So we can make an atomic, and then we have this fetch and add, like a fetch and incur operation on the atomic. And now this code actually type checks. So my question for you is, why is it safe to use atomic here, but it wasn't safe to use a rep? Why does an atomic provide that a reference does not?
Synchronization. Synchronization.
Synchronization. You got it right the first time. Right? It provides synchronization. And so it's safe to share it across all of these domains. And so because atomics, the type atomic provides synchronization, it actually crosses portability and contention, right? So this is our second instance of mode crossing here. So even though inside of our function, count is contended, we can read and write to it, or specifically this fetch and add count can exist because it's shared. And it's because it synchronizes the memory. Sorry.
Question?
Question.
What about the string concat?
What about the string concat? What do you think?
Well, doesn't that raise on the allocation?
Does it race on the allocation? So if we have two domains running and they both run a concatenation, they're just separate allocations, right? So we have two separate string allocations. And because the runtime is, multi-core aware, the runtime will safely have the allocation.
So that will be a hash operation. On the allocation point of it, it will actually need to do something special in the
There's different heaps for different domains.
okay, separate domains, separate heaps.
Yeah, so the OCaml 5 runtime takes care of that because the GC is do anywhere. So here the only race is the actual.
So that may come with a little overhead, right?
Is there overhead for that?
No, the pool steps are separate. So
Yeah.
each domain has its own separate
Different heap.
Yeah.
So we have different heaps for this allocation. More questions?
I mean, I think this is super cool. This is not a fixed level. I feel like the synchronization is slightly sneaky, right? I mean, the fact that it's synchronized doesn't make the code correct. It's the fact that you choose to use the fetch and add and also synchronize it. But you could read and write like you did in the old code.
Yeah, so what Alex is doing, I'm just kidding. I have an example in 5 seconds that's going to hit at us, right? We'll come back to that. That's a really good comment. Another question.
To his point, though,
Yeah.
about the separate domains, that's why you don't need to call atomic again, right? For the next function, for the the concatenation, right?
Yes. The only shared memory was the count.
Right.
Right. And so that memory needs to be synchronized. Here.
Yeah.
And atomic provides that synchronization.
Right. So I'm just like adding some context.
Yes.
To this question.
Yes. That's correct. More questions. These are great questions. Ask away.
So is contended only useful for synchronized in practice? Is it only useful for like compiler error messages and for synchronized values? Because otherwise it's always you can either something that you can't use or that is a mistake to use.
Either can use or is a mistake to use. So this is a good question, and I'm going to answer it with one more change to Jensen, right? So now in our code, it's called make Jensen, and we can optionally provide our own prefix. So instead of just gsim, we could provide another prefix. Now, when we do the string concatenation, we're actually reading the prefix. And that was closed over by this lambda. Is that your question here? Because now, it's shared, but this code compiles.
It's okay, it's shared.
It's okay. Well,
it's not contended.
Yeah, immutable.
It's immutable.
Yeah.
So this is another example of mode crossing, right? The string type is immutable. And so contended exists because somebody could be writing to that memory. But the type string itself prevents the writes. So we know that it is fine to read that variable. And so, for example, if you have a record and one of the fields in the record is mutable, but the other fields in the record are immutable, you can actually read from immutable fields because they mode cross along contention. So even though they're contended, we can read from them. Does that answer your question?
Yeah.
Okay, cool. These are great questions. Any more?
Yeah. So one more quick. This was for later to actually get the strings implemented in the stack, right? Because then you start having problems with.
So if we wanted to like locally allocate this prefix or something,
Yeah, or the result of the function.
So the result of the function we could do, right? Because that is just whoever called this function is in some domain where they have a caller, and we can locally allocate the string and the column if we wanted to. We couldn't, for example, locally allocate this prefix because that would be for this function, but we're returning the lambda which captures it. So that would be escaping its region. Does that answer your question? Yeah, okay, we can talk about it again. More questions from this side of the room. I feel like we're a little divided, but I promise. Yes.
Can you do anything with a contended value?
Can you do anything with a contended value? Contended mutable references? No. If it is an immutable reference, right? So like I said, if you have an immutable field of a struct, then you can read it because the immutableness of the type is preventing other people from writing. And so that makes it safe to read. That's good. More questions.
What happens if you don't put the at portable on some function? Let's say you have a ref, you have the unsafe version, and you forgot to assert that it should be portable. Because in regular OCaml you can, and OxCaml claims to be compatible.
Yep.
So how does this start?
How does it work? Right. So all of the examples throughout these slides have been in OxCaml.
I know.
And previously, we didn't expect Jensen to be portable because we weren't trying to send it across domains. The reason in these examples it needs to be portable is because we were using that parallel array.init.
So,
and that function asserts that the lambda it runs to initialize all the elements in the array must be portable. That lambda calls Jensen. Jensen must be portable.
So you're basically you have to write your part array in an OxCaml way. You have to rewrite that part. And then every time you use it, it's automatically going to check that you did everything.
It will check that all of those functions that you get it calls are portable.
But if you use the stdlib, the regular one, then unsafe things can still happen.
Then yes, then you're debugging for a really long time.
Yeah.
Yeah, that's true. Yeah, so if we didn't write portable here and we were still using ref, it's a non-portable function. So as long as we're just calling it on one domain and we're not trying to share it across domains, totally fine. You can do that. Your code. Question.
What if we are using a public, but we did not write portable?
Then as long as it is portable, it will be so it will infer this at portable. We didn't have to write it. I'm just making it explicit here. So as long as your function is portable, then we're good to go. No compiler errors. Yeah.
Okay, so OxCaml providing replacements for these types? Or like, is it the name the same thing as it would be in the standard library?
No, it remains the same thing. Yeah. So the thing that might change are some of the, the libraries exposed. So for example, if we want a function that returns a locally allocated value, that function needs to sort of be rewritten in an OxCaml way to allocate it locally. And if it, provides the type signatures, we'll have to write them. But they're like the basic module re-exports a lot of these functions with type signatures as well.
So is it the library author of init that has to say this has to be portable?
Yes.
What is so if the author of this library makes an error, then the users will also have data races.
Yes, if you have bad libraries, you also sort of inherit that badness a little bit. You get bad.
So compiling doesn't know that.
No, Chris is disagreeing with me. Listen to Chris.
OxCaml is going to prevent you from writing a database. But as long as you use, so one thing to say about Perk is that it has magic inside to be, and as long as you use the OxCaml provided libraries and don't use standard, then you will be unable to write a database. There's no way to do it. There would be no way to write parent it and expose it as long as you're building OxCaml libraries in a way that provides parallelism if it wasn't enforcing the work.
Yeah. So the question is, if I write this par array in normal OCaml and it's just an OCaml library and I use it in OxCaml, has no annotation, then yeah, you have a data race, but you should be using the OxCaml provided version of that library, which then you would prevent your data race.
That's no different from Rust. If you're writing stuff in unsafe, Rust will bet it's wrong.
Yeah, I mean, I can just write C code and unsafe Rust. I got daily pointers.
I could write C code and a camel too, it'll be like
yeah.
I'm more interested in a number of questions, which is if you've got a contended reference,
okay.
Presumably you can either return that or do a physical quality check on it. So look at the reference itself, not at the record, particularly its point of 13. And the other one was another fun pattern that Rust you can do is you will effectively
a function that allocates in the crawler's stack frame. How do you do that? Presume that you parameterize a function with the region into which the result is.
Yes, so
there's a difference between local meaning local line frame and local meaning local sum frame.
Yes. So that would be that exclave keyword that I mentioned earlier. So if I write exclave, it says, hey, allocate these things in your callers.
Yeah. Well, does it presumably it means that is that parameterized? That would be in Rust with what they call lifetime. I wouldn't say lifetime, then I need. So
yeah. In the current version of OxCaml, no. You use sort of a template PPX rewriting, so you can provide multiple versions. I've heard that.
Template PPX.
I've heard that this will change, and you'll have a nicer experience in the future. Currently, it's just with the template. So that's why we had to say like alloc stack when we called array init, because we wanted the version of array init that allocates.
So exclave is an exclave like Kaliningrad. That's depressing, just like I say,
not familiar with whatever you just signed.
Kaliningrad is a Russian exclave on the Baltic Sea, which is the western side of the Suwalki Gap.
So I think the short answer is yes.
We had a talk this morning about how if you say let in someone to freeze your objects, you weren't quite sure how far the Red Army would get. Anyway.
Good. All right, questions.
Can you allocate in your colors region?
In your colors region?
Yes.
Yes. So if you have
can you exclave?
No, so how it would have to work is both functions have to be cooperative, right? So if I have an exclave function and I'm calling a function that itself uses exclave, then that's going to actually use the colors stack. Right, and it's safe to do that, right? Because I have the call stack. You can just look up the stack code. All right. So I promised Alex this this example like 15 minutes ago, but here it is, right? So this code compiles, but we actually would have the same problem as before, because there is a race condition on the increment and the get of the count variable. Right? Atomics prevent data races because of the synchronization, but they don't prevent race conditions. You still have to write, good code in the sense. And the problem here is that the increment and the get should be atomic. Those two operations need to be atomic in order to have a good version of Jensen. All right, so to directly answer your question, Alex, yes, you can write this. Yes, it compiles. Yes, you'll still be debugging. But this is where we get to capsules. So if the atomic fetch and add function didn't exist, we can actually still write a version of Jensen here that does not have a race condition. So a capsule is going to associate some mutable state with locks that just ensure exclusive access. And then capsules are going to use the type system to track some stuff. They're quite complicated, but we're going to see a nice little example here. So we'll read through it together, I promise. So the first thing we do is we create a mutex that is going to guard our capsule data. And when we create that, we get this mutex value here, which is sort of the key to accessing our data. The second step is we then create our data. And we do that with this little initialization function. And here we're going to go back to using the bare reference. So we just return a reference with the integer 0 in it. And then we're going to write our own version of fetch and anchor right here. And what it's going to do is it's going to lock the mutex. We then get our access to that mutex. We access the data inside of the mutex, inside of that capsule, which gives us our bare reference. And then we do our increment, and then we read out the value. And now this fetch and anchor is atomized, and this version of Jensen goes back to being correct. It has no race conditions. Questions?
What stops you leaking access?
What stops you from leaking access? As in, Like, could I return?
No, access is a variable. Can I not just write it to a reference outside it?
Can I not write it to the reference outside the function? Modes. So we're going to use, like, this could be at the local node, and so we can't write it into a reference that escapes the function. So again, these modes work together to give us the safety in OxCaml that we want.
So what type is access got here for the
What type does access have here for the lambda? Truth be told, I have no idea.
So access is just a type, and it's actually void.
Okay.
It has no
Okay.
representation. It is just used to make the typing work. So it's basically like it's a permission to, or it's like a witness that you're in the correct capsule.
Okay. Yes. The longer answer is we updated this code last night to the latest version of OxCaml, and or this morning, whenever it was, and so I'm not entirely sure of all of the typing rules here, but yes. Question. This one. Yeah. Question.
Is there OxCaml studlib that isn't base?
Is there an OxCaml standard library that isn't base? I'm gonna defer that one to Chris.
Soon there will be a new standard library in OxCaml called Ox. I don't think that's in the version that's current.
Soon there will be a new version of the standard library provided with OxCaml. Yes. All right. Any more questions? All right. So I have been talking for a long time. We've been humming. We've been having fun. But I've prepared a little interactive activity for you all that you can sort of test your understanding of OxCaml as it currently exists. So you can either go to this URL, which is tinyurl.com, OxCaml-ICFP25-activity, or you can scan the QR code. I believe you can do it on your phone, you can do it on your browser.
I think I can give something.
Some people have network access.
Last name together.
Very successfully.
Yeah.
Yes, I think so. With what?
But it's just not on websites. Okay.
You seem to be. You got it?
I can do it on my phone? Okay.
Nice. You can do it.
Okay, awesome. Yes.
Hopefully it's big enough to read.
Quiz,
It should be.
really?
It is a fun interactive activity.
Not a
Way to
quiz.
test your own insights.
Press next, and then it goes to the next question. Right.
It will tell you at the end of all the questions.
Maybe I'm just getting all wrong here.
Would be getting more and more wrong. That is something you can do. I've done it myself.
Yeah, I started getting confident, but actually, no.
Yeah.
What is it?
Yeah, it comes with rugs.
Oh,
But it's fine.
Don't go on.
Creating a website that works everywhere.
we're really trying to.
Just like this.
If we give you half the diagram.
It's two hydrogen and cross the gases. Like it's in I want to get that. Another question, I didn't set the notes. But the numbers they talk about the issue of having multiple functions. Does that necessarily imply the parameter was multiple?
So if the parameters of function.
Yeah.
Then it would be portable.
Yeah. Yes, but
Right,
if
I mean,
it's like a record.
If it's like a record, so then it could be a pseudo, and
Then
as long as the record doesn't have function, it's.
Yeah, then it's.
Then you could say it's portable, and then it's, you know, then it goes to system.
So it was just the functional that
It's, yeah, so it does apply.
Yeah, in a sense, like.
They all have this, right?
Yeah.
So if we just have to.
Yeah, you have to go up the paintbrush, switch it.
There's actually comparative.
Yeah.
And so it is, if you prove, there's a few different things which we did. You could prove that the higher. Was yes, portable,
meaning that the function is part of the function, and then when we type it. Entirely is real.
Second.
That would you have on to us we actually so these the arguments that so the first one should so first implementation could actually say that's already into free presumably the implementation is from so something could still happen. So the interesting thing here about this dedication of the uniqueness is that along the control flow paths, they can be used as different. So the true range it's used as and then also we need to use those two the primary yes, that T is going to be because if we do call in the truth, it need to be relaxed. Then if the aspect runs, it gets turning totally.
So in terms of these, so when I annotate they can actually infer
it could, yes, it could.
And then use something.
So broadly, those are writing them down is just useful. Like if you expect something, then you say I expect this. I mean, it's the same way we spoke about functions.
Yeah,
right? They're all inferred, but sometimes I get weird inference errors. Okay, let's come back together. If you're not done, that's fine. You can finish our activity later if you'd like. But we'll just wrap up. So in its like this was a whirlwind tour of a subset of the OxCaml language. There's a lot more. There's documentation online you can go and read now with your new knowledge. We also have this tutorial posted online. There are code examples there where we give you or code activities. Right, we give you some OCaml code and we say make this, parallel OxCaml code, and you might have to rewrite it and add in annotations. We also have Anil has posted some information in the Discord. So we have a GitHub code space online that you can actually generate. So you don't have to install anything locally. You can just test it out online and you have a working version of the compiler and all of the tooling. If you want to do that asynchronously during the week, you're welcome to. And I will be at the Jane Street booth from 3 to 4 every day answering questions. You can also email me. You could also, if you really wanted to, come back to this tutorial session at 4 or whenever it starts. And Anil and Casey are here and they can help you write code. I will be giving the presentation to a whole bunch of other people, but they can take you and write code if you want. It is there. Thank you very much. More questions?
Just a question. If I'm not writing parallel nor performance critical code, do I actually care about OxCaml?
Do you actually care?
It's cool, but
it's cool, right? So in short, if you don't need any of the properties that OxCaml provides, then I mean, no, right? Like there's no reason you have to use Rust if you really want to use C++, for example.
Yeah.
But if you are doing these things and you want this fine-grained control over the performance of your code, then we have OxCaml. And then you can go in sort of the opposite direction. So Rust goes from like systems to safety. OCaml is going from like really safe and high level to the system side, right? So they're taking different approaches on that spectrum.
Also,
but it's not only performance, it's also concurrency, right? Like data arrays and so on. So
Yeah.
even if
But
you
I mean, if
write
you're not
performance
writing,
critical code, might still want to avoid data races, I guess.
if you're not writing any parallel code, then it doesn't matter. But Anil has a.
I am finding it quite useful to prototype code in OxCaml, then write it in OxCaml without the annotations, because then it's more portable for general use. But it's generally safer because we've used the more restricted types of OxCaml to put you down a good path to avoid data races in the future. So even for purely functional code, it's quite useful.
Can you use effect handlers in OxCaml as well?
Yes, we actually saw. So this like await.t, this is sort of like an awaiting capability because we're using the mutex here. So we need that capability because currently we don't have like the types effect handlers, but in the future, when we do have them, that could be just implicitly passed in, right? And then we have the effect handler for awaiting. We don't need it.
Or we can use it right now.
Right now.
Again.
Right now, yes. So you can go write that code. This code runs if you
As of
start
like
the code phase.
we clicked merged about last night, so
Yeah.
there's a brand new version of OxCaml.
As of 12 hours, you can write this code and run.
I
Yeah.
just want to give you the applause because we skipped over that.
Yeah.
More questions? We have them.
Oh, yeah, what we're going on, is that Richard's comment? To what extent is OxCaml directly, which way would be downwardly compatible with OxCaml? So, could you run your code through something that strips out all of these annotations? And then does that still run on the standard OxCaml or?
Not if you're using like, well, I guess if you strip out the annotations and the keywords and change libraries and things like that, then yes.
So I think some of OxCaml's extensions are straightforwardly erasable and some of them aren't. And in fact, Jane Street's internal versions of Basic 4 now use OxCaml. We run them through a version of OCaml format that does exactly what we suggested, strip out the annotations before we publish it. Some of the extensions though are not approved. No.
Yes. Slightly longer answer is that there's three different types of OxCaml extensions. The first one are things that are upstreamable to OxCaml. So there's features like labeled tuples and things which have actually just been put into upstream OxCaml. So they're in OxCaml 5.4, released about 3 days ago. Then the second set is the erasable ones, and then the third set are the really hard to erase ones. Things like locals and stuff. You just use local underscore, and then that just becomes an identity function in normal OxCaml, and you can just ignore it. But the parallelism ones are super difficult to erase.
The relevance, yes.
Just about the experience using it, the US users. So is that, would you usually write, the libraries that will use them in these features internally, and then at the external module level, you don't need to care much. How's the experience?
I'll defer that to the people who write it. Actually, I have very limited writing to do.
Yeah, I mean, I think there's been a lot of cases where we've went through and added annotations to a bunch of libraries internally. But then there's still a bunch of clients that use these libraries, which have been annotated, but don't actually make use of any of these OxCaml features that we talked about.
So the idea is that you only really need to use it if you want to, and if you don't want to, and if someone else is in their library, then they have to worry about it and you don't. In practice, it seems to play out mostly that way.
If everyone wants a really hard mode kind of problem, we've got this EIO library in OxCaml 5, which is a simple kind of concurrency fiber core. And I've just started porting it to OxCaml for fun. So it's a nice way to just re-implement the annotations from scratch in a new library that isn't Jane Street, just to get a sense of how to try it again. So if that was interested in that, we can just have a go at the fiber core later on in the next session.
More questions? No? Okay, well, more questions.
Yeah, I wanted to ask to which extent does the effort of porting the internal libraries and porting existing code into OxCaml pay off and benefits you get from having it role?
I'll defer. Do you have an answer to that, or should we defer to the
So the question was, to what extent does the effort we're putting into port our code to this?
Yes.
I mean, I guess it must pay off because we didn't just port the code to the new branch of OCaml. We wrote a whole new branch of OCaml to support it. I think it is. Yeah. I think it's definitely paying off. I mean, we frankly were not comfortable letting Jane Street software engineers write parallel OCaml programs until we could give them a way to guarantee that they didn't have databases, because that felt too risky to do in production software. And so now we have started to deploy programs that are parallel because they can put them without databases, and we think that's been precious. So despite the fact that it would take us a solid 2 years.
Okay, then one other question. Is this is the development of SPLASH' going on in a separate like research part of Big Street, or on the, I mean, is it like a
terrific question. The question was, is the development of OxCaml happening in a separate research product? And the answer is no. Jane Street has no separate research work. We have a team that works on the OCaml research, but we're not a research team. We are software engineering.
Okay, I mainly was asking how successful are you on like pitching this idea of doing OxCaml to the global Big Street people?
How successful? Yes. I think we're reasonably successful. I mean, first of all, the engineers use it and they like it. The engineers who are our users report that it is helping them in their day-to-day work. And I mean, they haven't fired me yet, so I guess
for those who didn't hear, the consensus is OxCaml good. They're still working on it. Engineers happy. Jane Street, no data races. So check. All right.
It's what, you know, when you're thinking about this, break up OxCaml into multiple pieces. So there's things like the local extensions and memory control and kinds for layouts. That's kind of one thing that lets you do things like take advantage of new hardware, so SIMD instructions and vector units and that kind of thing. And then the parallelism is to give you a counterfactual from, you know, upstream OCaml development. It has been really stressful getting people to port their sequential or formerly sequential code to parallel code now. So in the community, there's lots and lots of efforts to make this work, but really it's a lot of dynamic checking and thread sanitizers and that kind of stuff. And so it's really exciting to see the fact that there's also this really brave kind of attempt to bring DRF there as well, right? So that's very much still to be decided if the ergonomics work out, but the end result is completely worth it because we should absolutely be aiming for data race freedom, you know, as a basic kind of part of our language. But parallelism is a new thing on OCaml, so that's only just coming along now. Whereas local allocation and memory control, that's kind of a thing that, you know, is kind of always needed. And that came along much earlier and is much more mature in the language.
Why do we need stack and exclave? Can we not just infer based on the table position of the allocation?
I mean, for exclave, the thing is that like if there is a library boundary, if you want to keep separate compilation, you can't have it like you're just installing a library that someone else has written, and depending on how it's used by other intermediate library that you have, etc. You can't. You would have to do that whole program thing if you want to analyze all the call signs.
Could you not just annotate the return type of the function as local, and this infers the fact that you're always allocating to callers region?
Sorry, I'm just going to move forward so people can hear me. You are actually correct. So in our very first version of this, we only had the stack keyword.
Yeah.
And that meant its meaning was context dependent.
Yeah.
Like in a tail position, it meant exclave, and other positions it meant allocate on the stack. Our programmers found that really confusing. They didn't understand why stack meant some things in some places, and or actually it was local. Why local meant some things in some places and other than other places. It's also sometimes ambiguous. Like you can have a position that is both an allocation site and a tail position. So we actually did a lot of work to undo that choice and split into 2 units.
Okay. If the type system can like check if it's annotated local and it's able to check if it's not, and we'll give you a type here. Why don't we just like default to like and make everything local, and if it's near like promote it to global? Well,
I mean, there that's ergonomics, right? It's a bit like the Rust kind of choice. I guess OCaml has a GC by default, and then you choose kind of region control for performance critical code, unlike, you know, Rust, where you control the things and you build a dynamic allocation library on top of that. Just the opposite philosophy. It is really hard to use if everything's local. In fact, Raphael and I built a prototype of this in 2013, linear ML, and it was beautiful, but unusable.
If there's no more questions, join the Discord, fire up a code space. You can start writing code activities. But thank you so much. Like I said, I'm here all week. Come talk to me, talk to them. They're smarter than me, so talk to them, but you can also talk to me. I'm less than me. And we're all set. Thank you so much.